The physical pendulum. An object of any mass or shape that is oscillating about an axis, you can call it as a physical pendulum. We have seen many objects which oscillate about an axis. They may not have a regular shape or any masses will be varying. You have studied in your class about simple pendulum. Simple pendulum you have studying is negligible mass, and its size is also very small, or a negligible size and a negligible mass is hanging from a string, and this is the mass. It is hanging from a string of length L. It is oscillating about this fixed point, and you have to make sure that this angular displacement is very small. This is theta. Theta is very small. You have to ensure that. So when theta is very small, we can make an approximation. This is theta. This is also theta. When theta is very small, sin theta can be approximated to theta. Now you look at this pendulum that is oscillating. This is displaced from the mean position. At this point, if you look at weight equal to mg is acting vertically downwards. This is the tension T on the string about this fixed point, and this is how it is the oscillating. So the restoring force trying to bring this mass towards its mean position is a component of this weight which is acting in this direction. If this angle is theta, this angle is also theta. So this component becomes the sine component, and it is tending to bring it back in the opposite direction. So this will be minus mg sine theta, which is the restoring force trying to bring it to the mean position. And the component along this direction, which is opposite to W, is mg cos theta. This is the cos component. This will be the sine component. Restoring force F equal to minus mg sine theta. Since theta is very small, you can approximate sine theta to theta. It becomes minus mg theta. Now the motion of this pendulum is pure rotation along a circle. If this is making an arc S of a circle, then this arc S is equal to L into theta. L is this distance or length of the pendulum. Theta is the small displacement. So arc length S is L theta, or theta equal to S by L. Now I am going to make the substitution S by L in the expression for the restoring force. So here I will get minus mg S by L. Minus mg S by L. So this is similar to our F equal to minus kx, the restoring force, where k is equal to mg by L in this particular situation. Now let us see what is the torque acting. The formula for torque is R cross F. Here R means the length of the pendulum L. So this becomes L into F. F is minus mg sine theta and L. So that becomes minus mgl sine theta. Sine theta is approximately equal to theta. So this becomes minus mgl theta. Now the moment of inertia. Moment of inertia is ml square. Moment of inertia I equal to ml square, and angular acceleration alpha equal to d square theta by dt square, which is theta double dot. Now for torque formula is I alpha, where I is the moment of inertia. So substituting for I and alpha, I will get ml square by theta double dot. So instead of torque, I am substituting ml theta double dot. This is equal to minus mgl theta. I have substituted this. We can cancel ml on both sides. So you get theta double dot plus g by L into theta equal to 0. This is similar to our expression d square theta by dt square plus g by L into theta equal to 0. So this is representing the equation of a simple harmonic motion where the frequency omega equal to root of g by L and period t will be 2 pi by omega. Substituting for omega you get 2 pi into root of L by g. Now the general solution for the displacement theta will be, it is oscillating, it is undergoing sinusoidal simple harmonic motion. So theta will be equal to A sin omega t plus B cos omega t. This is the general solution. And theta dot or d theta by dt will be equal to, differentiate this once with respect to t. You get A omega cos omega t minus B omega sin omega t. Now we have to find out the values of the constants A and B. For that we will be applying the initial conditions. At t equal to 0, that means initial state, theta will be equal to theta 0 or theta dot, theta naught, theta 0. So at t equal to 0, sin omega t will be sin 0 which is equal to 0 and cos omega t will be cos 0 which is equal to 1. So making these substitutions, when we substitute this, at t equal to 0, theta you can call it theta 0. Theta 0 will be equal to 0 plus b into 1 or theta 0 equal to b. So you get the value of the constant b as equal to theta 0. b is equal to theta 0. Now differentiate theta at time t equal to 0. So d theta by dt at t equal to 0 will be d theta 0 by dt, that is substituting for theta 0 you get db by dt, b is a constant, so when you differentiate you get it as 0. So again substituting this value, theta dot equal to 0. Theta dot equal to 0 means this quantity will be equal to 0. And if you look at this expression, b is not equal to 0. Sin omega t will become equal to 0 because omega t is equal to 0. And you look at this quantity, cos omega t is 1 at t equal to 0. So for this whole expression to be equal to 0, the value of a should be equal to 0. So you got the constant a as equal to 0. Now we will go back to our general equation. This is our general equation. A value, you got the value of a as equal to 0 and b is equal to theta naught. So if this is equal to 0, what remains is theta equal to theta naught cos omega t. So you got the expression for the displacement of the simple pendulum as theta equal to theta naught cos omega t, where theta is the angular displacement.